In algebra, it's very common to look at the slope of a line, and we understand that that slope is constant for a line, and it represents a rate of change. So if you have any sort of application in real life that grows linearly or according to a linear function, then there's a constant rate of change there. In calculus, though, we want to look at how do you find the rate of change of something that's not linear. For example, here I have this parabolic curve. How would I find the slope, quote unquote, along here? And the way that you have to phrase that question, because the slope is not constant, it changes, is we look at the slope of the curve at a given point. So for example here, I want to find the slope of this parabola at the point a f of a. So how do we do this? Well, we're actually going to borrow techniques we know from algebra to figure this out. So what I don't know is how to find the slope at this one point. But if I pick a second point along this curve, let's say right here, and I'll call this point x1, f of x1, and I draw a line connecting those 2 points, I can find the slope of this line. Okay, these kind of lines are called secant lines. And that's a line that passes through 2 specific points along this curve. Okay, so I do know how to find that slope just from algebra, because remember the slope of a line is just the difference in your y-coordinates divided by the difference in your x-coordinates. So this would look like f of x1 minus f of a, those are your 2 y-coordinates, divided by x1 minus a, those are your 2 x-coordinates. And so I can get then the slope of the secant line. Alright, now I'm going to borrow this approach to find the slope at this exact point. And the way I'm going to do that is maybe now I want to make a second secant line that's a little bit closer and find its slope. And then I'll find a third secant line whose x-coordinate is a little closer to a and find its secant line. And I keep doing this until eventually those 2 points along the x direction are so close that I just hit that one point along my curve. Now this kind of line is what we call a tangent line. And the point of a tangent line is the slope of the tangent line represents the slope of the curve at that given moment. Okay, so this is the basic mechanics of how we get to a tangent line, but how do we calculate that slope? Well, if you notice, I'm moving my x-coordinates closer to a, and I'm looking at all the slopes of these different secant lines. It's like a trend, and the way we evaluate trends in mathematics is through the limit. So I can write that the slope of the secant line, the slope of the tangent line at x equals a looks like this. We'll call it m, the limit as x approaches a, and then we just have the slope formula here. Right? So this is saying you're looking at the trends as your x-coordinate gets closer to a of this. And what is this? This is your slope formula. And so we're looking at the slopes of these secant lines and seeing what they trend towards, and that's how you find the slope of your tangent line. Now, another formulation of this, another thing that may be useful is instead of considering this just as x1, what if I consider the distance between x1 and a? So in other words, I could write a as x1 as a plus some distance that I'll call h. And so now all I have to do is formulate all these x-coordinates as a plus some sort of distance. And so if I do that, I can replace my formula then, and let's let that distance between the 2 points go to 0, and we'll call that distance h. So here I'm taking the limit as h approaches 0, and remember my x-coordinates now are not x1, x2, x3, etc. It's a plus some sort of distance. So I have f of a plus h minus f of a all over the difference of the x's looks a little funny now. You have a plus h for the first x coordinate minus a for the second coordinate. And if you notice, a plus h minus a is simply h. So here we have two different formulations of the slope of a tangent line. And this is extremely useful because this tells me the rate of change at a given moment along the curve. And now notice this is parabolic, but there's nothing here that says that these have to be parabolic functions. We can take this tangent line idea to any function. All right, now this is such an important topic that we have a specific name for it. So when you say the derivative of f at x equals a, what I'm talking about is exactly this. The tangent lines, the slope of the tangent line is what your derivative is. It's the slope of the tangent line at x equals a. And I know the tangent line of f of x at x equals a is what I mean here. Okay, and the notation we use is this f prime of a. So when I say f prime of a, I'm talking about the slope of the tangent line of f of x at the point x equals a. And how do I formulate that? It's by a limit based upon the slope formula. Okay, it's a really brilliant idea. Now another thing we could do is, what if I didn't specify exactly what point I wanted? What if I found the derivative at all the points along this curve? Then could I do that? Do I have to go through this limit process over and over again? Well, not really. What I can say here is the derivative, and we'll call it f prime of x, of f of x, is, okay, the limit as h approaches 0 of f of x plus h minus f of x all over h. And now here I didn't specify what a was, so this actually turns out to be a function of x itself. So when you take the derivative, you get another function. Okay, we want to find the instantaneous rate of change of f of x equals the square root of x plus 1 at the point 3, 2. And so this is our example of how you can find a derivative, and remember the derivative gives me the instantaneous rate of change, or another way of saying this is the slope of the tangent line, okay, at, in this case, x equals 3. Alright, so we know from our formula that f prime, and I'm not going to just find f prime of 3, what I want to do is actually find f prime of x. So I'm going to specify x after I take this thing. Alright, and so by definition, that's the limit as h approaches 0 of the square root of f of x plus h. So let me write that first, actually. That's the limit as h approaches 0 of f of x plus h minus f of x all over h, which is another way of saying, so let's specify what our function is. The square root, I replace x first of all with x plus h minus whatever f of x was, which is the square root of x plus 1, all over h. Okay, now from here I cannot plug in h because I get 0 over 0. So I need to use some sort of algebra technique to solve this, and the trick to get rid of these radicals here is by multiplying by what we call the conjugate. So I'm going to multiply by x plus h, the square root of x plus h plus 1, plus the square root of x plus 1. And I can't just multiply the numerator by that, I need to multiply the denominator as well. Right? So here essentially I'm multiplying everything by some giant expression which equals 1. The reason this works so well is because, as you'll see in the numerator, when I FOIL, so I do need a FOIL here, distribute everything across everything. When I do that, a lot of things are going to clean up very nicely. For example, first I get the square root of x plus h plus 1 quantity squared, right? Secondly, I get a plus square root of x plus h plus 1 times a square root of x plus 1. That's not so nice. But if you notice, on the inside I have a minus square root of x plus h plus 1 times the square root of x plus 1. And so those two very ugly expressions subtract each other out. So that's not too bad. And then lastly I have minus the square root of x plus 1 quantity squared. All of this over h. Okay. And as I was saying, this does simplify because, again, these two subtract out. And here I have square roots squared, so that means I have the limit as h approaches 0 of x plus h plus 1 minus an x plus 1 all over h. Oh, and I forgot, this denominator is also being multiplied by the conjugate. And my recommendation is to not distribute or anything because it's not going to clean up for you until the end. So here I have square root of x plus h plus 1 plus the square root of x plus 1. Alright, now I see here in the numerator I have an x minus an x, and I have a 1 minus a 1. So all I'm left with then is h. Okay, so I can say here I have the limit as h approaches 0 of h over h times this expression in the denominator. And now my h's can cancel, and I'm left with the limit as h approaches 0 of 1 over square root of x plus h plus 1 plus the square root of x plus 1. Now I'm allowed to plug in 0 for h because I don't get anything, it's in the domain, I'm okay. So I end up with 1 over 2 times the square root of x plus 1, right? This becomes x plus 1, the square root of x plus 1, plus the square root of x plus 1. So that's 2 times the square root of x plus 1. So there's f prime of x. Now that's not what it asked for. It asked for the instantaneous rate of change of my function at this point. So at this point, all I have to do then is plug in 3. So I plug in 3 to my derivative, and that's 1 over 2 times the square root of 3 plus 1. And so that becomes, what, 1 over 2 times the square root of 4, so I get 1/4. There's the instantaneous rate of change at that point. Now the reason it's helpful to calculate f prime of x is because I could have a second example quickly. So how about, let's say, a b part. How about at the point with an x coordinate of 1. So that'd be 1 square root of 1, 1 plus 1, which is square root of 2. Okay, well I've already done the work. So here I just have to say f prime of 1, which is 1 over 2 times the square root of 1 plus 1. So that's 1 over 2 root 2. And so there we have it. There's the instantaneous rate of change at the point 1 root 2. And so now that I have f prime of x, I can essentially find the slope of the tangent line at any given point. I hope this makes sense. If you have any questions, please let me know. I'd be glad to help. And thank you for watching.